Hey everybody, this is Merker here from Noble 9, and once again, I'm talking to one of my tech friends, and I've got on the line here Matt Moore. Say hi, Matt.
Hi, Matt.
Matt's on at VMware, and he's one of the engineers on the Knative project. Maybe just tell the viewers here, both of them, what Knative is.
We basically looked at serverless compute and Kubernetes and what the sort of gaps were in order to create a serverless-like experience on top of Kubernetes. And originally it was sort of three main pieces: build, which was source code to container; serving, which basically handles request-driven compute, auto-scaling and whatnot; and eventing. So how do you bring events into the system? How do you trigger that scale to zero, scale up based on request compute, based on the events?
Got
And
it.
so the build part eventually sort of grew a mind of its own and spun off as Tecton. And so these days, Knative is largely serving and eventing, and we still like the Tecton folks, but they've sort of moved out of the house, so to speak. So
Matt, so before we got started, we were just about to tell me about the community call you had this morning. We were talking about reliability in Knative, and you actually have some charts you want to share, right?
yeah, so basically, in the name of reliability, I always like to sort of keep folks on their toes, and so every so often I'll try and sort of turn things up to 11 and see what breaks. And so over the weekend, I kicked off a script that basically what it does. Actually, I've got it up here, patent pending. It basically just says, okay, create a ton of services. So this is saying, okay, for I equals 1 to 1500, use our CLI to create a service with this tiny little Go image, and then sleep for 10 seconds between them.
And full disclosure here, we should probably say that you and I used to work on the GCR project, which you're using in this example, when we were both at Google.
Oh yeah, yeah. I'm particularly fond of GCR. It is, I don't know if I'm allowed to say it's the best registry anymore, but it might be. Uh,
Well, and just on that topic, when we thought about GCR as a product, reliability was the feature, right? That literally was the thing that made GCR the top performing from our point of view.
yeah, it was a lot of fun building that, and learning a lot. So yeah,
Anyway, back to the thing you were talking about.
yeah, back to yeah. I experienced zero GCR problems while running this experience or experiment. So yeah, so basically, what I did was I spun up a whole bunch of services, and what I was seeing is if you look at this, the x-axis here is basically how many services have been created so far. So as you create more services, you see that the little scatter plot, the dots get higher. So what the height of the dot represents is how long it took from when we created it to when it reported as ready. So the more services that we deployed, the longer it took for those to become ready. And so this is actually only 1,000, and we can get to that. But what the other thing we were seeing is, in addition to how long it takes to do that initial deployment, we're actually also seeing that the our cold start latency was also sort of trending up and lagging as well. So and it went from 2 seconds or so to like 12 seconds, which is actually about what we see this hop up over time once you reach about 1,000 services. And so basically, I started to dig in, and we discovered this service links thing in Kubernetes, which we had actually been. It's a feature that was added to Kubernetes ages ago to compete with Docker links, and one of the early service discovery mechanisms. But what it does is it sticks environment variables into your container for every service in your namespace. And so the more services you have, the more Kubernetes services you have, the bigger and bigger your environment gets. And so, 1,000 Knative services, we actually create a couple Kubernetes services under the hood. And so you end up with so many things in your environment that it actually takes materially longer to start up your pod. So basically, this picture down below is me running the same experiment. And I think this is only 1,000 services, but basically throwing the relatively new flag in Kubernetes, and it's about to ship in our Knative release on Tuesday, that disables the injection of these service links. It's enable service links false. And you can see that now deploying 1,000 services, right? Like it doesn't get any slower. And if you look at our cold start latency, it actually frankly, it looks better than it does with nothing deployed when we had those service links enabled. I think it's typically around 3 seconds when we had service links enabled before, which is the default in Kubernetes. And with them disabled, it's like 2 seconds and sometimes even under 2 seconds.
Tell me about cold starts.
Yeah, so cold start. So in serverless compute, right? The idea is you want to pay for what you use, right? And with request-based compute, right? What that means is if you're not getting any requests, right? Especially if you're doing event-driven stuff, and like, okay, I'm not getting any events, I don't want to pay for anything, right? And so part of how we do that is we scale you down to 0, right? There's no running pods when you're not, you don't have any incoming requests or any incoming events, right? So cold starts are when we've scaled you down to 0 effectively, and a request comes in and we don't have anything running and we need to start up a pod in order to service that request. And so that latency, that overhead on top of the normal just request response latency, if something were running, is what's referred to as the cold start latency, because you're cold, you don't have a running pod in order to handle the request, and you've got to start it up and then forward the request onto that. And sometimes, it can also refer to sort of when you need to add capacity, even once you're at a steady state. But generally, we try and sort of provision a little bit ahead so that you don't hit that outside of the sort of scale from 0 scenario.
Got it. Very, very helpful. And then another question I had for you: when you look at this this chart, it's kind of a linear growth that's happening here. Is your expectation that this continues, or do you think that you run into a scale cliff? And also, with the environment variables, it's kind of a really interesting, novel problem that the environment variables kind of snuck in there and started growing. Can you maybe share more about like how you came up with the hypothesis that was the problem, or what you did to debug that?
Yeah, so there were a couple little sort of clues. So I do think it's probably linear, and there is there was an interesting cliff. So I mentioned that that original loop was 1,500. This is only showing 1,000 because what happens is just about at 1,200 services, it fell off the cliff, and the environment grew so large. If I scroll up the error messages here, the environment grew so large that it actually the Go processes started failing to start. And I got this cryptic error message about the argument list being too long. I was like, I'm not passing more arguments. So that was one thing. And basically, this was a really bad sort of cascading failure, because not only could I no longer deploy new services, but existing services that have been scaled to 0, those pods wouldn't start either, right? Because all of the services that have started since those services were deployed are getting injected into the new pods for the services you cold start. And so basically, when you hit this state, I had something like 1,200 Knative services in my namespace, all of which were useless because you couldn't cold start them, right? And you couldn't deploy new ones. And so on a whim, I don't remember really what prompted me to do this.
Maybe your sixth sense. No.
Yeah, it was my sixth, maybe even my seventh sense um, that um, I don't have any maple syrup to chug, but uh, let's see. So on a whim, I decided, what if I try and create a Knative service in another namespace? Um, and when I did that, the deployment latency for that new service was surprisingly short. And I had noticed the longer cold start in the other namespace and the fact that the other services weren't cold starting. And when I switched over and I looked at um, the cold start latency of the service in that new namespace, it was actually quite fast, right? It was sort of what we have before. And so that told me it wasn't necessarily something about the number of services in the system in general that was slowing down the kubelet. It was telling me that it was something specific to how services in that namespace were being started. And because we had sort of actually relatively recently, we were just talking about service links 2 weeks ago in the same community call, because it was sort of fresh. I sort of had service links on my brain, and I was aware that service links, it's just services within your namespace that get injected as environment variables for discovery. And so I was like, okay, well maybe I'll try disabling that, because we had just introduced this the ability to pass that spec field through from the Knative service down to the pods we create. And when I reran the experiment, right, like everything was cool, right? And in fact, it was better than before if you look at our cold start latency. And
Yeah, I was just gonna ask you. It's really interesting, right? So, a couple things here that I think might be interesting to generalize, right? When we think about this as like a general approach, is there a way, without doing kind of what you did, to actually try to exercise the system that you could have, like, is there a test vector you could have done here that would have discovered this fundamental kind of scalability cliff without actually exercising the system, or is this the kind of thing that kind of is a sales pitch for why you need to do load testing? I mean, what do you think about that?
yeah, so I mean, it's a really interesting question. I mean, I feel like I feel like, in a perfect world, right, you would be so deeply aware, and have just penetrating X-ray vision to see through all of the layers of abstraction to know how everything works. But I feel like, you know, a lot of these things that until you push them to a certain scale and see how they fail, you can't anticipate everything, right? And so, I, honestly, I don't know that I've ever seen a process fail to start up because of something. I've seen the command line too long, right? Because I think I've heard of people patching kernels so that you can pass even longer, command line flags. But I hadn't heard of it failing because the environment had grown too large, and it just hadn't really occurred to me until I saw and was debugging this. So that and service links, because they were added so long ago and are such a sort of uncommon way of doing service discovery in Kubernetes these days, a lot of folks don't even realize they're there. So until you like dump your environment and you're like, what is all this stuff that's been sort of getting stuffed into my containers runtime. In fact, the discussion we had 2 weeks ago was sort of a cosmetic one. It's like, well, Kubernetes is stuffing all this junk into my containers environment.
Not pretty, right? It's not pretty to have all my environment variables. But you make a really interesting point, because I imagine the downstream application developer, let's say, who they or cluster admin or SRE or whatever, right? The operations person, and you just imagine this situation. It has nothing to do with the application, right? It has nothing to do with their mode of deployment. It has nothing to do with their cloud. It doesn't actually have anything to do with even really design choices they've made. And unless they had actually put it through the paces, because it exists, several layers below their code. So when we think about sort of engineering for reliability, testing, the value of kind of trying these things out. I mean, if you were an on-call and you got this cryptic error message, as you said, in a real scenario, not a test, what would life have been like in that scenario?
Yeah, I mean, it would have been rough, right? This what was nice about sort of what I had set up here was like, okay, it was a very controlled experiment, right? But if I had been doing this, you know, if in production I had deployed my 1200th service and all of a sudden like the whole system died, I'd be freaking out, right? I mean, obviously in those situations you'd want to, you know, have good sort of rollback practices, right? But you know, honestly,
But the rollback in this scenario wouldn't have actually necessarily helped because as soon as the 1200th service is deployed, can you scroll back up to the linear growth picture? Because another thing just occurred to me. I want to ask you your thoughts on this.
yeah,
I agree with you that there's this cliff, right? There's this cliff at 1200, but there's another way of looking at this, which is if you had a low tolerance for creeping latency, then you could have avoided it becoming an outage. What do you think about that? What strategy can you use there?
yeah. So I mean, I think it's definitely interesting to track latency and this sort of slow growth of you know, increasing latency. And I think that's always one of the hardest things to sort of monitor for and track. You know, there's so many different dimensions to this kind of slow, or that might contribute to this sort of slow growth, right? Like, well, I'm adding features, my binary is getting bigger, my container image is getting bigger, it consumes more memory at runtime, it's loading, you know, more information in at startup. There's so many different factors that could contribute to it that it's natural to sort of discount it as sort of the natural evolution of things. And so, but like, you know, if you are super sensitive to this, right, like uh, it's really critical that you track it and understand why things are growing. And you know, it's unfortunately really easy to get desensitized to why it's growing after you've investigated it, and it's that same root cause time and time again. Oh, well, my binary got bigger, my container image got bigger, and so it's a little slower to pull, or you know, it's a little slower to start up or whatever. But like, you know, it could be that like, okay, I switched from Go 113 to Go 114, right? And there's some sort of regression in the language around, you know, startup performance or something like that. But you know, it's, you know, I think it's one of the nice things about having really good tracking and continuous delivery is, you know, the smaller the changes you're rolling out at any given time, right? It's easier to track down where those sort of those blips occur, and you know, if latency jumps up on the commit where like you switched from, you know, one version of Go to the next, or you pulled in some new dependency, etc. It's you know, a lot easier to sort of, you know, sort of pops out at you. Whereas, you know, if you roll out once a quarter, good luck, right?
Right.
Uh, so,
So,
and some of
so
these things,
maybe. Oh, sorry. Go finish.
oh, yeah, I was just gonna say, some of these things really like until you sort of are rolling them out to production and have that telemetry coming back from, you know, real user load. You know, sometimes unless you have an environment set up that, you know, you think really um, represents sort of your production workload, you know, I that always sort of makes me smile because you know, there's really no substitute to production traffic in terms of like being a signal, right? So that this the stories I'm reminded of even go way past me working with you at Google, right? Like I remember doing back when I was at Microsoft, right? Like profile guided optimization, right? I wanna train my program on like the ways people will use it, so that I can have the compiler make those like really fast, right? And you know, it turns out we're really terrible at predicting and creating training load workloads for you know, what are representative of how folks actually use things. And there was this really funny story where I forget what version of Windows, but they were training it, the you know, Windows, and they were running it through this process, and certain web pages were really slow to load. And when they dug into it, it turns out that like web pages that had like JPEGs were really good, and web pages that had like GIFs were really slow. And it turns out their training set didn't have GIFs in it. So like they were basically telling the compiler, hey, this stuff doesn't matter. And so the compiler was, basically sticking it out in the boonies where, okay, this code's never executed. I'll put it in cold storage. And so, I think, that very long-winded way of saying, I think that there's really no substitute in those scenarios for actually having pretty good visibility into how folks are actually, using your system, and sort of telemetry coming from that feeds into situations like this. You can try and reproduce it in contrived ways like this, but this was a very focused experiment trying to exacerbate one particular way to stress the system.
Right.
Which
So,
yeah.
was there anything else you wanted to show me on this page, or do you think that scrolling down?
No, so I mean, I pushed it up to 1500 after it all worked, and we opened some issues against Kubernetes because this isn't specific to what we're doing, right? This just has to do with cramming a ton of stuff into a particular namespace, and Kubernetes itself, right? Because underneath Knative, we're just creating, what we're doing a little bit of magic, but like when we're creating pods, we're just creating pods, right? And it was the creation of pods that was slowing down from like 2 seconds to like, 12 to 13 seconds. So, and then ultimately falling off the cliff and failing to start completely. So, but yeah, I mean, 1500 with this thing disabled, it's pretty flat and evenly distributed over the sort of range of startup latencies that we see.
So based on this expected behavior, you could set up some sort of monitoring that would look at this, because now that you don't have this linear kind of linear slowdown with a cliff, you could set something like that. And is that something that you work with other people on the project to set objectives for the goal? Like, would you say 15 seconds is showing up here as kind of the a maximum extreme beyond, but maybe there's some other interesting distributions of points on here. How do you think about setting the kind of goals around latency targets?
So that's a really good question. So this is one of the, so there's a whole bunch of dimensions where we are tracking latency of a whole bunch of different things. It's mostly around, it's mostly around our sort of data plane latency, right? So how slow are cold starts? How quickly can we respond to really big spikes in request volume from zero, as well as we have tracking of the sort of our contribution to data plane latency overhead. So if you were to sort of peel the onion of our data plane, Kubernetes services, right, are sort of our theoretical limit. If you're hosting a service on Kubernetes, right, the Kubernetes load balancer at sort of layer 3 is, let's say the baseline, right? You layer on top of that, going through an L7 layer like and the ingress resource, going through a layer of envoys provisioned by like Istio or Contour or Courier or
any of the service meshes.
Yeah, any of those. It adds a hop, right? And then we have two other layers in there. We have a sidecar that we inject that we call the Q proxy, and then we have another layer that we inject when we are scaling you to zero, right? It's a shared component that we route requests through. And we use that as sort of a meat shield. So whenever your service is sort of under provisioned, it's on the request path to protect your service from a big spike in traffic. And that can sort of buffer the requests as additional capacity is brought online. But so we have these really cool graphs let me stop sharing this and I'll try and pull it up quickly. We basically have ongoing sort of tracking in the community around these metrics. And so one of the things I was talking about was how, we have these layers of, hops in the network that we go through in order to reach your actual application code. And so what we're looking at now is those layers, right? And it looks almost exactly what you'd expect, where we don't have any of our sort of serverless style throttling. So like with Lambda, it throttles things so that each application instance is only dealing with a single request at a time. And so we have a knob that tells you, that lets you say how many requests to let through at any given time. This is basically just saying YOLO, let through as many as you want. And so what we're really looking at is effectively the network topology, how many sort of hops we're going through. And so at the bottom, you can see I'm hovering over here, and if you look in the box down here, when I'm hovering on it, it says 0.1008. So this is seconds. So at the 95th percentile, talking to the service we have deployed, and it's the same service in all these cases, it's 100 milliseconds. So the application is very sophisticated. It sleeps for 100 milliseconds. So you can see that the overhead of Kubernetes in this case is about 0.8 milliseconds, right? Because the overall latency end to end is 100.8 milliseconds. If we add one hop, right, and we go through Istio, right, that bumps up to 2 milliseconds of overhead reaching the service. When we add in our Q-proxy sidecar, in addition to those other layers, right, it's about 2.6 milliseconds of overhead. And then when we add in our activator component, it's 3.4 milliseconds of overhead. Now, where this starts to get interesting, and actually this blew my mind when we started to invest in this. I expected this sort of to be the stacking of the data, just like that's the way it is. The number of hops you go through, that's going to translate directly to latency. But it turns out,
makes intuitive sense that would be the case.
Yeah. So so it makes sense, but that assumes all of the levels of load balancing are sort of dumb, right? And equally good, right? Because all of these are sort of probabilistically load balancing. And so if you look at, this is, I believe this is looking at, let's see. So this is looking at container concurrency 100. So effectively no throttling, right? We're letting through 100 concurrent requests at a time. And so we've basically set it so high so that the throttling's enabled, but it's not really ever going to effectively do anything. And it looks basically identical to the previous graph, right? They jitter a little bit, but not super interesting. So the next graph, it flips it to 10. And so there's something really subtle here, which is the activator graph, which is at the top here, which is the most hops, actually is faster with container concurrency 10, and it's way faster when you go to container concurrency 1, right? And so what's happening here is our Q proxy, the reason it exists is when you're routing traffic directly to pods and you're doing random load balancing, you aren't going to be able to with naive load balancing in front, you aren't going to be able to make sure that only one request is hitting that. So if you were saying container concurrency 1 and you're doing things like, YOLO, I don't need locks, the system's going to keep it so that I don't get concurrent requests, which is actually a really nice thing when you're trying to reason about, global state. We have that there as sort of a last line of defense, but what it does when it gets additional requests is it queues. And so what you see in this case, right, is requests when they're randomly load balanced at the 95th percentile, they queue up a little bit, and the overhead is this hits about 300 milliseconds of latency, which means you're waiting at the 95th percentile for 2 to 3 requests ahead of you to complete. right? But so there's a member of our community from Google, Victor, who spent a whole bunch of time actually building really sophisticated sort of concurrency aware load balancing into our activator component. So when requests are flowing through that, even at container concurrency 1, you end up with this really tight bound of, what is this, 3.7 milliseconds of overhead because it's doing virtually ideal load balancing. Um, and so, container concurrency 1, 10, 100, and unlimited, you actually get pretty good load balancing characteristics. And that inversion just blew my mind the first time we started to actually do some of this stuff, and it made me really happy. So these are fixed provisioning. We're not scaling up, scaling down. This is sort of intended to be pure sort of network latency. And I think for this we're sending 1,000 QPS for a couple minutes, but it's provisioned so that it doesn't have to scale up or scale down. It's in fact, I think it's clamped so that it won't scale at all. And so it's measuring sort of pure network overhead here. But we wanted a benchmark that also looked at basically how we deal with load. So let's see, if I switch to logarithmic, I think we can see all the lines at the same time. This actually overlays, in addition to our sort of request rate data, it overlays latency data. It also overlays a few other metrics that are sort of interesting. So this green line up here, basically what this benchmark does is it has a service that's been scaled to 0. It sends 1,000 QPS at it for, I think, about 2 minutes. And then it doubles that to 2,000 QPS. And then it adds another 1,000 QPS after another 2 minutes.
Just for people who don't know the acronym, QPS stands for what?
Sorry. Queries per second, RPS, requests per second. So so we're basically running a load generator and sending 1,000 requests every second for the first 2 minutes, then 2,000, then 3,000. So that's these steps you see here. And it starts at 0 with the service scaled to 0. So I don't think there's any errors.
Is this service the same? Is this the same service that's just the Sleep 100, or is this a different test example?
Yes. I think we pretty universally use the. We can actually look at the latency here once. So if we sort of filter the data, you can see that the latency of the requests that start real early is about 2 seconds, and as capacity comes online, the latency drops, and it's about 100 milliseconds here. So yeah, we're using that same sleep 100 milliseconds image.
With that first kind of steep curve there that's dropping, that blue line curving down, that kind of represents your cold start situation a little bit, right?
Yeah, exactly. So the way we basically track cold start latency is we actually look at this scenario and we say, okay, we're starting from 0 and we're scaling that up with 1,000 QPS. And so we're not just measuring like, okay, send a request, tell me how long it takes. We're actually sending a few thousand requests, and we are over this entire benchmark saying, well, our cold start latency is the maximum request latency for this entire run. And that's what we track. And so it's not like, okay, P95, it is like the maximum latency we see over this entire benchmark.
Do you have a goal for that latency? I mean, is there a goal that you set, or is just you want to see what it is?
Yeah, we do. I don't have it up, and it's probably not tight enough. Mako has some analyzers that will sort of trip alerts and stuff when you cross certain thresholds, and it's got some more sophisticated things that if you just have a one-off outlier won't raise alarm bells and whatnot, but yeah, we have some thresholds set, and basically if we cross them maybe for a couple runs, it will open an issue, and I think it'll ping us in Slack too. And so we can see sort of over time what our you know how our cold start latency is trending, and we also look at error rates and things like that. I think so. This orange and brown line, these are I believe desired and actual pod counts, and you can see that right where we step up to 2,000, we add another pod, and then when we step up to 3,000, we add another two pods. But yeah, so I mean, these are the kinds of things that we are tracking, and I want more of the control plane stuff in there, but yeah,
Awesome.
we haven't. It hasn't landed there yet.
Very cool. Thank you for sharing that.
Okay.
So we spent a whole bunch of time doing show and tell on charts, which I we didn't plan it, but it was kind of fun. I liked it a lot. But maybe we can switch gears just for a few minutes before we drop off. So one of the things I think it's on some people's minds these days. I'd love to get your take on this. People earlier in their career trying to get involved in open source, trying to get involved in engineering. People who are maybe intimidated by technology or just starting out in computer science. What do you think about what they should do? What's your advice? Like if you were going to talk to Matt Moore of 15, 20 years ago and say, hey kid, this is what you need to do. What do you say to the next generation coming up?
That's a really good question.
And I didn't mean to spring it on you with no preparation. I just
No,
want
no,
your
no.
reaction.
Uh, yeah. So I think the main thing is, as a more senior engineer, I think the thing that a lot of junior engineers, they have this misconception that like we've got all the answers, right? And I think we have a lot of experience and we have intuition that we formed around performance, reliability, whatnot, what works, what doesn't, and I think there's a lot of things where like there's the saying, right, like no is temporary, yes is forever, sort of things, right, where people you say not now and people hear no, right, and it's like, well, yeah. So I think that it's not bad to make mistakes. It is not bad to ask the dumb questions, right? Like honestly, if you're in a place where you feel like you can't ask those kinds of questions, right? Like I think that's harmful to your growth, right? You need to be able to ask those kinds of dumb questions, right? Because people, I don't care what engineer you're talking to, right? They don't have all the answers. They are not always right. Honestly, I think that I've seen, I've seen organizational disasters happen before because a senior engineer was like, I think we should do this, and we still live for folks to push back on us and challenge us and engage in debate. And at a certain point, you have to start being careful about being too vocal about some of those opinions and like bold statements, because a lot of people will take them at face value and be like, "Oh my God, we got to go do this." Turn the.
But to your point, Matt, when we look at and reflect back on how senior engineers behave, right? And I think this is an interesting twist to the story, right? Which is, it sounds like there's also feedback to the senior engineers in the equation, because maybe they don't realize, and maybe what they say doesn't meet all cultures, or all mindsets for people coming to it. What do you think about that? What's your advice to senior engineers to be more inclusive and welcoming?
Oh, it's really tough. I mean, I think I've seen a whole bunch of people have different strategies, and frankly, like not all those strategies work with all audiences either, right? I think I know people who are super self-deprecating. I know people who I think especially right now when we're all working remote, lots of Slack and whatnot, there's really no substitute for sort of human contact and, stop going back and forth, writing, a wall of text in Google Doc comments, right? And just hop on a call, humanize it. Um, I think that often works. It is harder once you start to talk about geographic distribution and stuff
Sure,
like
sure.
that. But yeah, you know, it, I think that there are a whole bunch of strategies you need to develop, and it depends a lot on sort of the context of your working situation. But uh, and I one of the things I miss in quarantine is being able to grab some of the folks that I work with and grab a whiteboard and a cup of coffee and draw pictures because I'm pretty visual, and I have to say we as a technology industry have failed at advancing the state of digital whiteboards to the point where I don't have one on my wall. So
Well, Matt, we're just about out of time. We're gonna have to leave it there, I think. And I really appreciate it. It was a lot of fun. Do you have a good time?
yeah, this was it was fun to chat and show the fancy graphs. Hopefully, we'll have even more if we get invited back.
And if people wanted to get in touch with you, or they wanted to join in on Knative or learn more about what's going on, what's the best way to get in touch?
We are extremely active on Slack. Slack.knative.dev. I think we'll get you an invite link. I'm Matt Moore, no E, Mattmoor. So feel free to ping me on Knative Slack, or join one of our channels, and it's a fun bunch.
PR is welcome.
Ah,
Joking,
yes,
joking.
but PR is welcome, but issues welcome, right? Like asking for help welcome, right? I it's I don't know. It's a fun bunch of folks that we've gathered together, and honestly, contribution takes many forms. Some of it is just using the product and giving feedback, right? So if it doesn't work for you, I'd like to know about it, and uh, yeah.
Perfect. Thanks, Matt. Take care, man. And everybody
Yeah.
out there, thanks for watching. Hope you stayed with us the whole time, and we'll see you next time. Thanks.